In this unit, we will be discussing integration by substitution. There are two types of integration by substitution. The first one is by algebraic substitution, and the second is by trigonometric substitution. Before we discuss examples of integration by substitution, let me give you the integrals of inverse trigonometric function. The integral of du all over the square root of a squared minus u squared is equivalent to the arc sine of u over a plus c. The integral of du all over a squared plus u squared is equal to 1 over a arctangent of u all over a plus c. And the third one, the integral of du all over u times the square root of u squared minus a squared is equal to 1 over a arcsecant of the absolute value of u all over a plus c. And always take note, in using integration formulas, du is always the exact differential of u, where u is the variable of integration. In integrating by using trigonometric substitutions, there are three cases to be considered. If the integrand involves the square root of a squared minus u squared, substitute u to be equivalent to a sine theta. Taking du, it gives a cosine theta d theta. If the integrand involves the square root of a squared plus u squared, substitute u equals a tangent theta. Taking du, it gives a secant squared theta d theta. Third, if the integrand involves u squared minus a squared, we substitute u to be equal to a secant theta. Taking du, it gives a secant theta tangent theta d theta. Take note that a is the constant term while u is a variable function or the variable of integration. Let us evaluate the integral of the square root of 9 minus x squared all over x squared dx. This integrand shows a difference of two squares, a constant minus a variable. This function cannot be readily integrated by using the earlier formulas that were introduced. So we will try trigonometric substitution. The difference of two squares here resembles a squared minus u squared. That is the 9 minus x squared found in the integral. So this will suggest substitution similar to u is equal to a sine theta. The constant term in this integral is a squared equals 9, so a is equal to 3. The variable function is u squared equals x squared, so u is equal to x. For the substitution u is equal to a sine theta, we use x to be equivalent to 3 sine theta. Taking the differential, it becomes 3 cosine theta d theta. Substituting x is equal to 3 sine theta and dx is equal to 3 cosine theta d theta in our integral, it will give us the integral of the square root of 9 minus 9 sine squared theta all over 9 sine squared theta multiplied to 3 cosine theta d theta. If we simplify further, this becomes the square root of 9 times the quantity 1 minus sine squared theta over 9 sine squared theta times 3 cosine theta d theta. If we further simplify, 1 minus sine squared theta is an identity equivalent to cosine squared theta. So we get the integral of 3 cosine squared theta over 9 sine squared theta times 3 cosine theta d theta. Further simplifying gives us the integral of cotangent squared theta d theta. We can integrate this by using an identity where cotangent squared theta is equal to cosecant squared theta minus 1. And if we expand, it gives us the integral of cosecant squared theta d theta minus the integral of d theta. We already have direct formulas for this. So we get negative cotangent theta minus theta plus c. Negative cotangent theta minus theta plus c is not yet the final answer. We have to return the variable x in the final answer. So we have to construct a right triangle for our reference. Since we use the substitution x is equal to 3 sine theta, we could say that the sine of theta is equal to x over 3. Solving for the angle theta, this will be equivalent to the arcsine of x over 3. Constructing our triangle, basing it from our substitution, sine theta is equal to x over 3. The definition of sine from trigonometry is the ratio of the opposite side over the hypotenuse. So this will be the triangle. X is the side opposite angle theta and 3 is the hypotenuse. The third side can be computed using the Pythagorean theorem, wherein that side becomes the square root of 9 minus x squared. If we look into the triangle, if we solve for the cotangent of theta, which is a ratio of the adjacent side over the opposite side, we get the square root of 9 minus x squared over x. So therefore, we will now substitute the value of cotangent theta and theta into the temporary answer, which is negative cotangent theta minus theta plus c. If we substitute these values, we get our final answer as a negative of the square root of 9 minus x squared over x minus the arcsine of x over 3 plus the arbitrary constant c.